Nice to see you. So it's
nice
a really
good.
It's a really pleasure for me to be a speaker in this meeting, not only for a celebration of George Preston, because you know, he's always inspiring us, but in particular, I would say to find a big family of people that are interested in Ararlaire. And these, for the time being, is not easy to find these kind of communities. So I am very happy about that. So in preparing the talk, unfortunately, I didn't contact before Barry, because otherwise I would have changed the title of my talk, talking about epiphenomenal problems in Ararlaire, because my talk is essentially on how the metallicity impacts the properties of the Ararlaire. So at the very end, you will see whether it is worth the game, is worth the candle. But let me move on and show what are the three main points that I would like to touch during my talk. In particular, I would like to talk about the work that we have recently done with a number of people, in particular for a PhD project of Juliana Crestani, but in collaboration with many others. In particular, I would say that played a key role, both George and Chris, and you will realize in a minute why they have been so important. So just this is a kind of slide that I always introduce when I have talks with the extragalactic community to make sense of what we are doing. And in this case, I would like to make sense of the Ararlaire as a stellar beacons to investigate what are what have been the physics and the phenomena that have driven the early formation of the galaxy, and to discriminate between different models, not necessarily the monolithic collapse of the hierarchical models, but there are nowadays many other important and relevant issues concerning the Ararlaire. In particular, I would say a number of long-standing problems, in particular the impact that major majors, minor majors have had, the mass budget of the fraction of the stars that have been formed in situ in our own galaxy, and the fraction that has been accreted. And the same applies also to the time scale at which this kind of accretion took place in our galaxy. And there are a number of relevant questions that we have to address in order to make sense of these overall big question that we have about the formation of our galaxy. And the main effort in investigating these kind of problems is essentially the question that you can see on top of on the bottom of my slide. That is essentially what is the kind of stellar tracers that we can use to address these kind of questions. And there is no doubt that right now, at least for what are our knowledges of these phenomena, that the best tracers are the Ararlaire. And the reason is very simple, because they are direct, they can provide direct evidence. They are older than 10 gigayears, and this means that whatever is their origin, they always are tracing the old stellar component, okay? The same does not apply to red giants, because the red giants can be produced by a huge fraction of stellar populations compared to Ararlaire. So what they are providing is quite often indirect evidence, because whenever they have been accreted, until we do not know very precisely what is the distance modulus, what is the metallicity, what is the reddening, we cannot estimate with some accuracy what is their age. And so the effort in using the Ararlaire, that are very demanding objects, is the fact that according to what is the current and the evidence, they are always tracing an old population. Okay, so let's move on And it is clear that nowadays, you know that in a couple of days, there will be the release of Gaia DR3. And according to preliminary news that are available on the web, it seems that they are going to release a catalog of 10 millions of variable stars. And well, there is a plausible guess that a significant fraction of them might be RR stars. So they are popular, but they are going to become even more popular after this release. And this is just to tell you, just to mention that together with the RR Lyre, there are other tracers, in particular the type 2 Cepheids that, as Horace has already mentioned, have mainly old progenitors, and so they share the same pros that the RR Lyre have. But let me move. I am pretty sure that you know very well all these information about the RR Lyre. Let me show what we have done during the last 3-4 years. That has been to collect a photometric catalog, including all the variable stars available in the literature. And they go from ASAS, Catalina, Gaia, ZTF, all kinds of possible sources that have provided RR Lyre have been included in our catalog. And what is important, all of them have been scaled to the asymmetric solution of the Gaia. So this means that we have identified twins, triple stars that have been discovered several times, and they have only a single entry in our catalog. And it is clear that in this huge effort, we are including dwarf galaxies and globular clusters, stuff that is already available in the literature, but now is in a single photometric catalog. Okay, but you know, this is something that is, I would say, classical. The main issue, the main problem that we have always in dealing with the RR Lyre has been the metallicity, because we have a solid evidence from stellar evolution that the mass and the luminosity are tightly correlated with the metallicity. And so our effort was to collect a huge amount of high resolution spectra collected with a bunch of high resolution spectrographs available all over the world. And in this game, in this effort, the DuPont spectra collected by George and collaborators have been fundamental, because they have quite often a full coverage of the pulsation cycle, and you will realize in a minute why these kind of data are quite important in the effort that we are interested in. So just to give you a few numbers, we are talking about 400 high resolution spectra for 162 field RR Lyre, and what we are dealing with is almost 1 order of magnitude larger than any other investigation available in the literature. Note that in this kind of analysis, we are including the stars that have already been observed by George and Chris and Shadid and collaborators like FOR. They are considered belonging to the same sample, because we are using the same approach for providing the abundances of these objects. So when I am quoting these numbers, I am including their objects as well. But what is more important is the fact that we collected a huge number of low resolution spectra from the Sloan Digital Sky Survey and from LAMOST. And you can see here that we are not talking about tens, hundreds. We are talking thousands of RR Lyre for which this kind of information is available. And so what we did after the huge pioneering work done by George in the late 50s and by Andrew Leiden in the 90s, we performed a new calibration. Juliana performed a new calibration of the delta S method. And now the delta S method can be applied to any pulsation phase, can be applied to any kind of RR Lyre, including C-type and AB-type, whatever is the pulsation amplitude, whatever is the position in the instability state. Okay, so this is a significant step forward compared with what was available in the literature till a few years ago. Now, there are a number of technicalities. In case you are interested, I can answer your questions. But what is important, is that the data coming from the high resolution sample played a crucial role, because for the first time we have high resolution spectra covering the entire range of metallicity of the RR layer, which means almost from -3 to above solar. Okay, and this is a fundamental point whenever you have to calibrate something. You need to have good data for the calibration. So now let me say that globally we have something like 11,000 RR layer. Among them, 9,000 are good enough to estimate the metallicity. 11,000 are going to be good enough for the measurement of the radial velocity. And you know, whenever you have a sample like this one, you only have to sit and try to dump all the peoples that are in your shoes, because you have the possibility to address a number of relevant problems. So let me quote the first one. If you go in the literature, it seems quite obvious that the RR layer have to be metal poor and metal intermediate. But now you can see that we have a bunch of RR layers, both in the high resolution sample and in the low resolution sample, that are approaching solar. And this is, you know, when you have these numbers, it cannot be just a matter of, you know, peculiarities. This is fully supporting the results obtained by Chris, and in particular in a paper obtained long ago, provided long ago by Allister and Turndrup about the bulge RR layer. Something that is quite important here, I forgot to mention before, the RR layer I am talking about have been selected to have a galactocentric distance larger than 5 kiloparsecs. So we are not including RR layer that belong to the bulge, essentially RR layer belonging to the halo, okay? Now, there are another long-standing problem was, for example, whether there is a difference in the metallicity distribution between A, B, and C type. And we found this difference. And this difference is predicted by evolutionary models, because the morphology of the horizontal branch is affected by metallicity. And when you are in a more metal poor regime, you are more prone to produce C-type RR layer than you are producing in the metal-rich regime. But let me show this, that is very preliminary, and once again, I don't know whether Andrew is connected, but this is fully supporting a result obtained in his PhD thesis, and is the fact that there is no metallicity gradient, at least in galactocentric distance. The top panel, the omega is the projection on the galactic plane, onto the galactic plane, and Z is the distance above the galactic plane. And as you can see, there is a mild evidence only in the Z component, but the mean metallicity of the galactic halo seems to be very close to the value that he obtained using a sample of 200 RR layer. But what is impressive here now is that all the previous estimates were limited around 30 kiloparsecs, and now we are approaching well beyond 100 kiloparsecs. By the way, this is also telling us that we have a solid evidence of RR layers that are well beyond what was considered a sort of a boundary for the galactic halo, but not only for the spectroscopic sample, but globally, we can say that right now we have solid evidence of RR layer approaching 140, 150 kiloparsecs from the galactic center. Okay. Now, since this is a very popular argument, in the last 80 years, it is clear that whenever you have a sample like this one, you are going to understand what is happening for the Osterhoff dichotomy. And there are different plots of the same problem. I was quoting here the sentence from directly from Osterhoff, or this is a modern version prepared by Matteo Monelli and Giuliano Fiorentino, in which there are included halo, globular clusters, and dwarf, and what was considered the Osterhoff dichotomy. I am not going to explain what is the Osterhoff dichotomy. But what is impressive is this figure that we published the last year, in which we use the 6,000 RR Lyrae. We only selected the RR Lyrae that do not belong to streams. This is the reason why the sample is slightly smaller than the global spectroscopic sample. And what you can see from this plot is that there is no dichotomy. There is no change. It's just a continuous variation from the metal poor to the metal rich regime. And we have been able to find an analytical relation describing the variation of the period and the variation of the luminosity amplitude as a function of the metallicity. So the question, the huge question that remained for 80 years, who is causing the Osterhoff dichotomy, is now becoming why globular clusters that are at metal intermediate metallicity didn't produce RR Lyrae. And as you can see, this is a question that is completely different from the original question. There is nothing weird with the RR Lyrae. What is weird is the problem of the second parameter problem, where is the second parameter problem that is affecting the morphology of the horizontal branch. And we have a number of globular clusters that are metal intermediate and in our own galaxy, not in the Magellanic Clouds or in other systems, that are not producing RR Lyrae. So as you can see, once you have good data, you can properly fix what is the problem, not just to have, the idea to have a problem. Now we are more precise on what is the big question about the properties of the RR Lyrae, cluster RR Lyrae. Okay, but whenever you start to scratch the something new, you always have curiosities, and this is another huge curiosity, because together with the mean period, another parameter that has been used for almost 50 years to dictate the difference between Osterhoff 1 and Osterhoff 2 has been the ratio between C-type RR Lyrae and the total number of RR Lyrae. And as you can see in these, this is my last, one of my last plots, so I am very, very happy about this result. And as you can see, the solid curve is just the running average over the entire metallicity range of the RR Lyrae in the spectroscopic sample. And on top of these, there are all the globular clusters with more than something, I don't remember whether a few dozen of RR Lyrae, and also in the next slide, I will also show the dwarf galaxies. And as you can see, the field RR Lyrae have nothing to do with the cluster RR Lyrae. The RR Lyrae, they have an Osterhoff dichotomy, but what the field RR Lyrae are showing is a continuous variation. And this continuous variation apparently is not going in the same direction suggested by evolutionary models, because what we would expect is a steady decrease in this fraction when you move from the metal poor to the metal rich regime. Okay, so what we decided to do in collaboration with Maurizio Salaris was to compute hundreds of synthetic horizontal branch models. We obviously used theoretical predictions for the instability strip to identify the C-type, the AB type. The predictions come from have been computed mainly by Marcella. And obviously, once you have all these predictions, what we have to do is to validate them. And how we validated these predictions? Just using the period distribution. So we know exactly what is the period distribution. They are not affected by distance, not affected by reddening. And so we validated the synthetic horizontal branch models, including the RR Lyrae with the period distributions. And once you have done this, I'm going to answer one of the points raised by Barry in the last few minutes of his talk. What you obtain is the present day mass distribution for the RR Lyrae in the instability strip. And as you can see, the mass distribution is decreasing from 0.8 to 0.55 when you move from -2.5 to 0.5. And if you have this kind of mass distribution, now you can see that you have a very good agreement between theory and observations concerning the population ratio between C-type and AB type. Now, here we also included the dwarf galaxies, just to go back to the point raised by Yabi, I guess. And as you can see, they are in the expected region. They seem to be in between the Ostrov 1 and Ostrov 2. But once again, what we observe in the halo is something that is quite different as a function of the metallicity.
You have 3 minutes. You have 3 minutes, Giuseppe.
Wow. Okay. So what we have here is no more iron over H, but is M over H, because we used the information obtained by Juliana concerning the trend of the alpha elements with the iron. And I do not have time to discuss all the other issues. We know what is the age of the progenitors. So we know the present day mass, and we can estimate what has been the mass loss all over the metallicity range. And what we find is that there is a tight correlation between metallicity and mass loss. The mass loss is increasing as soon as the metallicity increases. And we have compared with these results with reddening laws available in the literature from Origlia, Tailo, Savino, and some time ago also by Raffaele Gratton. And as you can see, there is some agreement in some metallicity regime, but no one of them is able to justify the entire metallicity range. So I do not have time to go here in detail. I only would like to show a single slide here. We have found evidence, and in this game, Chris was really fundamental to validate all the measurements that Juliana performed, a population of RR Lyrae that are metal-rich and alpha-poor. This was not expected at all, but you know, the numbers are becoming solid, and it's not just a matter of a few objects. We find a consistent trend over the entire metallicity range. And the similarities with the Sagittarius, this has already been published. We have many other results about iron peak elements, about neutron capture elements. The work is in progress. She moved in a different field, and so we hope that pretty soon we can publish these results about the neutron capture elements. And I will stop here and take your questions, but let me just mention once again that I am very happy to be a speaker in this meeting, to thank George for his incredible work over many years. I don't know whether there is a period of 60 years, but in any case, he really did a wonderful job in building what we know, the current knowledge of the RR Lyrae, and we are just fixing, you know, a few paintings, a few stages, but the big frame for sure relays on what George has done during so many years. So thank you very much.
Thank you, Giuseppe. Any questions from the audience for Giuseppe's talk? All right, I'm gonna look online. Oh, Anna, go ahead.
Thank you. Thanks for the talk. I have a question about that population of RR Lyrae at the 100 kiloparsecs that you were showing on. So it looks like there is like a little bit of a break, and so I was wondering, whether this is something physical or maybe just something related to the selection function of your survey.
Thank you very much for the question. Is mainly related to selection function, and I will tell you why. Because the bulk of the experiments are, let me go here. The bulk of the experiments concerning variability are mainly have a limited magnitude that is around V19, 18 and 19, and only a few of them have a limited magnitude that is beyond 20. But we realized that this is not due to a stream or a single experiment. There are a few of them that are distributed across the 4 quadrants. So it's not due to a single group or a single possible evidence of a stream. So there is a selection bias, but is evidence that they are distributed almost everywhere. Just to give you an idea, they mainly come from Pan-STAR, from DECAM, and from other surveys that cover the smaller area, but they have had very, very faint limited magnitudes.
All right, thank you, Giuseppe.